Good morning, good evening, good afternoon, wherever you are on this planet, people of Earth, and welcome to our SETI Live. Today we are going to talk about an exoplanet, one specific exoplanet called Gliese 12b. You may wonder why we're going to talk about this specific exoplanet, knowing that we have discovered already 6,000 of them and more than 7,000 of them are candidates. So this is probably very special. And to explain to us why this is a special exoplanet, we invited two researchers who have been working on a paper published recently on this interesting body. Hello, Larissa. How are you?
Hi, I'm good, thank you. How are you?
Good. Where are you calling us from?
Today I'm calling you from Edinburgh, Scotland, where the sun is slowly setting.
Okay. Larissa Palethorpe, she's a doctoral student at the University of Edinburgh. And with us, we have Shishir Dolakia. Hi, Shishir. How are you?
Hello, I'm doing good.
So, Shishir, are you in Australia right now?
Yeah, I'm from the University of Southern Queensland in Toowoomba, Australia.
And you are calling us from there?
No, I'm actually in California right now.
I was surprised because it's daylight on both sides. So it would be weird. All right, cool. So, let's go directly through this conversation. I mean, we have viewers watching us from plenty of places around the world. Tell us where you're watching us from, and we will mention maybe your city, your country, and say hi to you. Okay, so my first questions, we have two people here. So it's always good to know who is doing what. So you publish a paper together. Apparently you met already in person. How did you describe your role in this paper, in this analysis, in this work?
So we were actually co-leads. We've met once in New Zealand, but when we started this project, it was only ever via Zoom that we knew each other. And it was kind of born out of the fact that my team had a successful CHAOPS, European Space Agency proposal, and then so did Shishir's team. And then we came together in a collaboration, and me and Shishir were co-leads. We led the modeling together. So we were responsible for taking the data, kind of working out what kind of planet it was. And that was our main roles, really.
Okay, I like that. So you basically met in a conference, and both of you presented work, and from this you collaborated on this interesting paper. So Shishir, tell us about what the paper is about. What technology, what instrument did you use to do this discovery of this exoplanet?
Yeah, so the planet was originally discovered with the NASA's Transiting Exoplanet Survey satellite, which looks at large portions of the sky and looks for planets as they cross their faces of their star and cause minute dips in brightness as they block out a little bit of light.
Okay, and so I'm gonna ask you a very weird question because I really want our viewers to understand this. You find another Earth-like exoplanet, or what is it? Is that something you took a picture of it? It's like, what is this exoplanet? Why is it so special?
I wouldn't say this is exactly Earth-like. It's something similar to Earth. We'll say it's Earth-sized, and it gets in between the amount of light as Earth and Venus. And we haven't taken a picture of it directly. Rather, the NASA's TESS satellite is looking to infer the presence of these kinds of planets by, again, looking at that little dip in brightness that happens as this planet blocks out a little bit of light. And based on the amount of light that it blocks, we can tell that it's probably Earth-sized. And based on the fact that we see a dip in brightness every 12 days or so, we know the orbital period is around 12.7 days for this planet.
Okay, so you have not seen a biosphere, you have not seen dinosaurs, nothing like this.
Hold your horses. I think we're really far away from finding any evidence of life still, but we're thinking of this as like an exciting first step to study whether habitable conditions are possible elsewhere in the galaxy.
Okay, so Larissa, if you want to describe to us Gliese 12b, okay, tell us the characteristic.
So it's been hailed as our nearest transiting temperate Earth-sized planet found to date. So those are kind of the 4 key characteristics, and I'll break that down. So it's nearly 40 light years away. So that's not actually near. You couldn't pop there for a cup of tea, but it's close enough. It's one of our closest exoplanets. It's near in astronomical terms. And then transiting. So like Shashir just said, it passes in front of its star, which means that we can tell a lot more about the planet because it does that. Temperate in terms of it's about 42 degrees Celsius, which I think is 106 Fahrenheit, kind of its surface temperature. So it's not mega hot or mega cold like you see with kind of other planets. And then it's Earth size. So we put it in our paper about 1 Earth radius. So kind of the exact same size of Earth. It could be probably about 0.9 to 1 Earth radii. But that's, I think, very exciting to find a planet the same size as our own. So those are the kind of key features of what makes it so exciting.
Okay, we're gonna dig a little bit more into this. First, I want to say hi to people viewing us from Venus. That's Richard. Thank you, Richard, coming us all the way from Venus. You have an internet there. Then we have someone from, I love when you put the city and I cannot even pronounce this. Links from the UK, in the UK. There's a lot of jokes, okay. Kansas City in Manila, and Grand Prairie in Texas, London, small city, Lincolnshire in United Kingdom again, New Jersey in the US, Cambridge, UK, Canada, Houston, Texas, Savonlinna in Finland, and more UK, someone in Mexico and in Arkansas. Thank you. We are talking about Gliese 12b, an interesting, okay, let me rephrase that. Temperate, transiting, very close, Earth-size exoplanet. Okay, so we know the size, we know the location, we have an idea of the orbit. What can you tell me about this exoplanet beyond that? What about the atmosphere? That's what we expect to see for an exoplanet and its habitability.
We don't actually know what the atmosphere looks like, but it's a key question that we're trying to answer right now. So one of the things that's exciting about this planet is that the atmosphere is very characterizable because it's so nearby and because it's bright and because it's so amenable to observation with something like the James Webb Space Telescope. So if we were to point this telescope at Gliese 12b, we will be able to understand whether it has an atmosphere at all, or and if so, what kind of atmosphere that might be. We can get the chemical fingerprint of the atmosphere and figure out whether it's like a Venus-like atmosphere with lots of carbon dioxide. We can figure out if it's like an Earth-like atmosphere with lots of like nitrogen and like possibly oxygen, and we can also figure out if it's something entirely different as well.
Yeah, it could be a Mars without almost an atmosphere. Could be Mercury and of the Moon, completely dry without any atmosphere. Yeah, that's interesting. So that's the first step. So basically, KOPS and TESS, they look for those planets. You find them, you analyze them, you write a paper about them. Now you have, I'm assuming, an orbit, very accurate orbit, so you know when it's going to transit exactly. With an uncertainty on what? Can you get? What's the period basically, and what's the uncertainty typically right now?
The period is 12.76 days. I think our error on it, you might have to correct me, Shashir, was like 0.0005 days.
Okay, yeah,
Sounds
so it's quite accurate. All right,
it's quite precise.
So we can time now when the next transit will happen, the next transits. So you are going to ask for JWST, the James Webb Space Telescope time, and take advantage of this mid-infrared and near-infrared capability to take a spectrum. Is that the goal?
Ultimately, I think that the next step we're trying to do right now is work out the mass of the planet using radial velocities, which is kind of when the planet orbits the star, it kind of tugs on it. You get little wobbles, like the Doppler effect, the same way an ambulance sounds different coming towards you versus away from you. And from those wobbles, we'll be able to work out the mass of the planet. And then with the mass and the radius that we already have, we can then work out the density. And already at that stage, we can then infer things about the planet's composition and then JWST. But actually, we have already had a successful Hubble Space Telescope proposal, which will also be able to tell us things about the planet's atmosphere.
Okay, for the determination of the mass, you using a ground-based telescope to do this kind of analysis, I'm assuming?
Yeah, so there's been successful proposals to Espresso, which is in Chile, and also HARPS North, the HARPS North collaboration, which is another radio velocity telescope in La Palma in the Canary Islands, both working on it. But these measurements take you have to do them over a long period of time. So maybe a year until we know that.
Okay. So then we're gonna have the density. We'll know, for instance, if the density like Earth, typically 5 grams cc, or it's something more fluffier like Neptune or something like that, which is unlikely because it's very close to the star. But yeah, let's talk about the star. I'm seeing people joining us from Cyprus, California. Welcome. You're talking about Gliese 12b. So Gliese 12b, the name comes from Gliese 12. There is a star, right? So tell us about what we know about Gliese 12. What kind of star is that?
So it's an M dwarf, red dwarf star. And these stars historically are kind of quite active. So they tend to have long periods where they're very quiet, and then they get these massive super flares. And to compare those kind of flares to Earth, they tend to be like 100 to 1,000 times stronger. So which isn't great for habitability. But actually, Gliese 12, even though it's a red dwarf, we've characterized as being quite a low activity star. So that's kind of quite promising in that aspect.
Do we know the age of this star?
We do.
Yeah, we have a loose understanding of the age. It's probably somewhere around the sun's age, like 4 to 5 billion years, depending on who you ask. But it is a famously difficult problem to figure out how old M dwarf stars or red dwarf stars are. So that could be plus or minus 4 or 5 billion years. So it's really hard to say.
Yeah, that's a problem with this type of star. Generally we estimate the age by measuring the amount of lithium in the star, or by looking at the proper motion and whether or not they're part of a group of stars that were born together and kind of dispersing, right?
Yeah,
that's the way.
Quite technical, but yeah, absolutely. In this case, we can't do either of those things because lithium depletion, or the method of lithium depletion that you were talking about, is pretty challenging for M dwarfs still. And in addition to that, it isn't part of any open clusters or moving groups that we know of. So I think the best estimates of the age come from the fact that it's low activity, and we think that M dwarfs kind of just get lower activity as they age, but also from the motion through the galaxy. There's a way to say basically the faster it's moving through the galaxy, the older it's likely to be.
Okay, thank you. So yeah, this star may have had some very eruption or a strong activity, and seems to be calmer now. So that's a good news for the potential existence of life on this exoplanet, right? Do you want to discuss this with me?
Yeah, a lot of planets have been observed around M dwarfs with the James Webb Space Telescope, and so far many of them, especially the ones that are truly Earth-sized, have not been found with atmospheres. And we think this is because many of them are around really active red dwarfs, and have had their atmospheres blasted away by these super flares Larissa was talking about. And so we think that we don't know how active Gliese 12 has been through its history. Maybe it was super active when it was young, or maybe it wasn't super active. So by studying the atmosphere, we can also get a sense for how the star's activity history might have been, and to figure out whether more kinds of planets like this out there might actually be able to have atmospheres, or may not have atmospheres.
Larissa, you want to mention add something to that?
Yeah, I mean, everything Shashir said is true. We tend to find kind of a lot of smaller exoplanets around red dwarfs just because they're cooler and dimmer. They're more kind of amenable to the transiting method. So to find kind of one that we deem to be low activity, at least right now, could teach us a lot about other planets we've discovered without having to go through the whole JWST pipeline, because that can be quite slow and competitive. So this, is a really exciting target for a lot of different reasons, essentially. Okay, so we talk about Gliese 12b. I mean, you are
grad students. You're doing this work, searching for exoplanet, I'm assuming.
Mhm.
Can you tell us what you do on a daily basis? What exactly is the work you work on a daily basis, and what are the challenges? What is the most difficult part of your work as an astronomer searching for exoplanets? I'm assuming that this is the topic of your thesis.
Yeah, yeah. So a lot of the work that I do is around data analysis from satellites like TESS. So a lot of that involves the physics and the math in order to figure out what the data is telling us and what the models that we need to apply to the data are, right? And then the computer science to take the data and apply those models to the data, right? And then a lot of other things on the side as well that have to do with um, uh, analyzing the resulting data and the models and figuring out what's going on. And I would say that the challenge is in a lot of situations, the data will throw you a curveball. I guess that happened with Gliese 12b because when it was detected in the test data, we actually didn't know the period. So it could have been either 12 days or it could have been 25 days. And there was an ambiguity because one of the transits had fallen very neatly in a gap in the data. And so there could have been a transit there, but if there wasn't a transit there, it would have been a 25-day period instead. So we actually had to propose for a different telescope, the Cheops satellite, to make a little observation in order to disambiguate between those two scenarios. And that was actually like both my group at the University of Southern Queensland and Larissa's group had that same idea. So we both proposed for the same space telescope. And then that's kind of how we started our collaboration, because we both realized that we had the same idea and that we were on the same track, and it would be really fruitful to collaborate. So it was a cool little example of when the data threw us a curveball, but we ended up like forming a collaboration out of that.
Nice.
I will add as well that it's somewhat of a challenge. It was good collaboration, but being on opposite sides of the planets made arranging Zoom calls quite difficult.
Yeah, we had collaborators from all over, like from the US, from the UK, from Europe, and from Australia, and working out those time zones was quite difficult.
Yeah, I know this problem way too often. We're gonna take some questions from the audience. We have viewers from everywhere in the world, so let's take a few of them. Mathematica. I read somewhere the mass of Gliese 12b is 4 times greater than Earth. Is it true, or you don't? What do you think? Is that a real result, or that's a paper that's been published already? What is that?
So there was another team who also published on the same day as us, who I think were mainly based in Japan, and they already had some radial velocity mass measurements from a telescope. I think in their paper, basically, they could only really constrain an upper mass limit. Mm-hmm. And I think that's where the 3.8 or around there comes from. So we know that it's not bigger, it's not heavier than that, essentially. But I guess... So in terms of inferring things about its interior already, it's kind of hard because it could be 3, it could be a lot smaller, and models tend to change quite rapidly around that size range. So until we've got a more precise mass measurement, we can't say too much right now.
Okay. We have a question from Patricia Jardine. Does this newly found planet have any moons?
Tough ask. Tough question. I would guess that the answer to that would be no, although we don't know. But planets like this are often tidally locked. So that means that they experience a tidal force, which is basically the force from the star on the front of this planet is stronger than the force on the back of the planet. So the front of the planet always sort of is tugged to face the star. And so it sort of like spins so that it only presents one face to its star. And another consequence of that is that any moons or satellites around it would also experience those same tidal forces. And that means that in general, planets that are closer to their host stars tend, we think, not to have moons or satellites, although it's really difficult to actually detect those. So we can't be sure about that. But even in our solar system, Mercury and Venus don't have any moons or satellites due to tidal forces, likely.
Good. Another question from John Hart. Will a red dwarf cast red light onto its planet? Larissa?
Yes, I think to some degree. Essentially, there's a famous example of a red dwarf planet, TRAPPIST-1e.
One.
Where they say kind of in terms of like photosynthesis as well, it could happen at a different wavelength. So you could get kind of red plants rather than the green we like to think of. But yeah, essentially, great question.
Okay. A question from Richard T. He wants to know if Earth-sized planets orbiting a red dwarf likely to have an atmosphere. We already talked about that, but let's answer this question specifically.
If you were to ask my opinion, like the scientific fact is that we still don't know. We have some hints that yes, they are less likely to have an atmosphere because of this activity. But there's so many factors involved in trying to figure out whether they might have an atmosphere. And I could just list some of them. One is like the orbital period and how much light they receive from their host star. So if we look at the TRAPPIST-1 system of planets, there's like 7 planets in that system that Larissa was talking about earlier. The planets that are close in, we think have either very thin atmospheres or no atmospheres. But we're still sort of making observations of the planets further out that people think if there are any planets that are going to have atmospheres, maybe it's those ones. And we don't know yet, but early results seem to suggest that they don't. They're consistent with no atmosphere still. I will say the TRAPPIST-1 system is extremely active, whereas like Gliese 12 is actually very low activity. So maybe there's a possibility that this planet could have an atmosphere and might have held on to its atmosphere after the early flaring that Gliese 12 might have had. But yeah, still a very active area of research. And since red dwarf stars are the most common stars in the galaxy, and Earth-sized planets around them are really common, answering that question will help us understand whether Earth-sized planets around really common stars could be habitable or not, because we think an atmosphere is necessary for habitability.
Okay, a good answer. Larissa, you want to add something before I switch to the next question?
Yeah, I was just going to add that in terms of an atmosphere, kind of even if a planet is tidally locked, as Shashir was saying earlier, if there is an atmosphere, it could kind of help to regulate temperature across the planet. Otherwise, you're going to end up with a really hot side and a really cold side. So kind of working out whether Gliese 12 has an atmosphere is a really exciting moment. So I'll be keeping a close eye on all the work that's going on with the planet. So yeah.
Good. Question from Tao Ao from New Hampshire. I love this question because I like ground-based telescopes for multiple reasons. So he wants to know if the ELT, the extremely large telescope, the 40-meter class telescope that we are building in Chile, will tell something that we don't know already about this exoplanet and others.
I guess like right off the bat, I think that telescopes like those could provide really precise radial velocities that might be able to help us really quickly find the masses of planets like this and get them very precise as well. Larissa, do you have any other thoughts about what something like that could do?
Yeah, that's true. Because right now there's kind of a radial velocity floor. So we do purely discover planets through the radial velocity method. Its transiting method is more common, but right now it's really hard to discover an Earth-side planet through the radial velocity method because of the precision of our telescopes, but also because of how active some stars can be. Stars can mimic RV signals, and so you have to really be able to kind of pick them out. So the better our telescopes get, the better our science is going to get. So hopefully when it's kind of up and running, it will teach us a lot more.
Okay, so we have 3 more questions. Let's provide a quick answer. Laborious cretin. Oh God, names people. Do you know if there is phosphorus in the atmosphere of this exoplanet? I'm simplifying the questions here for you.
Short answer, no, not really.
Okay.
Yeah, we'll learn about stuff like that with JWST, but specifically, it's probably unlikely that we'll be able to detect phosphorus in an atmosphere like this. It is a threshold for basic life, but we think that it might it's likely that for rocky planets, there's a lot of different elements in the composition of these kinds of things. So I would place my bets on there's at least some phosphorus, but we have no idea.
Okay. Mathematica, is Gliese 12b visible from Earth?
The planet, no. The star, yes.
The magnitude of the star is 12, right?
Sorry?
The magnitude of the star invisible is 12.
Yeah, so it's in the Pisces constellation. So you should be able to see it, but the planet itself won't be giving off light, so you won't be able to see it, unfortunately. But the star, you can still look at the star and imagine it kind of lapping its planet every 12 days.
With a telescope.
Yeah, that being said, if you do have a large enough telescope, you can detect the transits from the ground. And indeed, we've done this with several ground-based telescopes around the world. The planet only blocks something like 1 part in every 1,000 parts of light that the star gives off. So it's a tiny dip in brightness, but it might be doable with telescopes like maybe something larger than half a meter or so.
Okay. Well, we're gonna end this very soon. So I have 2 questions. So first of all, how will you name this planet instead of Gliese 12b? Do you have an idea?
I like that some people have been calling it like a hell-like Venus.
Okay.
That's the pessimistic version of what it could be like, but I do like that as a name.
Yeah, I haven't really put any thought about what I would name it, but I kind of like the framing of it being like in between Earth and Venus, because it receives in between the amount of light that Earth and Venus receives. So I'm interested in like the concept of using it to like bridge the gap between Earth and Venus. So maybe something along the lines of like Earth and Venus's triplet, because Earth and Venus are called twins in the solar system.
Aye. So have you ever imagined when you were a young student, the little Shishir and the young Larissa, that one day you will discover an exoplanet? What's the feeling?
No, it was exciting to kind of have a big moment in science that everyone was talking about. Was really exciting and gratifying, because a lot of hard work goes into this by kind of a very big team as well. So the fact that people get excited about it who aren't scientists, but I never imagined it.
Yeah, it's been pretty surreal. Having like a NASA feature for something like this has been excited my inner child, definitely. Like since I grew up being super obsessed with NASA and like reading all of this stuff, and having like one of our papers feature prominently by them is something that's been really cool.
Cool. Congratulations, both of you. I think it's a great discovery, and it's good you do that when you're doing your PhD. I mean, it's a very motivating. I'm sure you're gonna finish this PhD, right?
I sure hope so. Yeah.
Fingers crossed.
Still a ways to go though.
Okay, so what's the future for you? What's the next step?
More planets.
More planets?
More planets. I'm interested in studying other kinds of planets around red dwarfs, but also I'm interested in like characterizing this planet further. Maybe with the space telescopes I was talking to you about earlier. I think we're both interested in doing like radial velocity type observations of this planet. And there's all sorts of other kinds of exoplanet science that I'm interested in.
Yeah, agreed. Yeah, definitely want to know more about this planet. That's the ultimate aim, but also to kind of look further at all the other planets similar in size. Can they teach us more about composition? What I really want to know is how unique is the Earth? That's what I want to understand. That's my ultimate aim.
Well, thank you very much to both of you. Thank you for taking the time to talk to us and to tell us about Gliese 12b and a bit about how you discovered this exoplanet. Thank you to all our viewers, wherever you are on this planet and Earth. I see that Julia sent the stars on Facebook. Thank you very much, Julia. This was the SETI Live. So SETI Live is part of the SETI Institute. We can follow us on all social media, all platform. If you like this video, you're watching us right now on any of these platform, click like, take the time to write comments, questions. We read them and sometimes we answer, and sometimes we even ask the scientists to help us answer to the questions. You can support our programs by going to seti.org/give now, or you can also simply register to receive our newsletter, tell us about our program, how we could improve it, and we will support young researchers like Larissa and Shishu, and they will come to the SETI Institute to work with us and find life on exoplanets. Right, guys?
Hopefully so.
All right, excellent. Thank you again, everybody, and see you next week. I forgot what is the program next week, but it is going to be as fascinating as this week. So see you next week. Bye-bye.
Bye. Thanks for having us.
Bye.